Hello, today we are covering measuring angles and arcs. You guys will be able to identify central angles, major arcs, minor arcs, and semicircles, and find their measures, as well as measure arc lengths. So our new vocab here is central angle, arc, minor arc, major arc, semicircle, congruent arcs, adjacent arcs, and arc lengths. So let's jump in. A central angle of a circle is an angle with a vertex in the center of the circle. Its sides contain two radii of the circle. And angle ABC is a central angle of this circle here. Notice it's really just an angle with the vertex at the center that extends to the sides of the circle. So if you recall from lesson 1, a degree is 1 out of 360 of the circular rotation about a point. This leads to the following relationship. So, the sum of the measures of the central angles of a circle with no interior points in common is 360. In this case, we can take angle 1 plus the measure of angle 2 plus the measure of angle 3, and that equals 360 degrees. All right, so we're going to come back to stuff from the very beginning of the year to solve these things. So, to find the value of x here, we actually have too much information. If this guy and this guy were actually vertical angles, which they are not, you could have said 5x plus 5 and then added them all up and equaled them to 360. But because we can't do that, they're not vertical angles, I instead am just going to use half of this. Now, if you recall, a line was equal to 180 degrees, so we can have 8x minus 4 plus 13x minus 3 plus 5x plus 5 equals 180. This 20x is actually extra information that we don't need. We can go ahead and combine like terms. And solve. So we end up getting 26x minus 2 is equal to 180. Then we go ahead and solve. So we get 26x is equal to 182. And then when you divide this out, you end up getting that x is equal to 7. Okay? We'll have another one like this. Find the value of x. Notice we don't have to plug it back in. We just are finding the value of x, not the measure of the angle. Make sure you pay attention to what it asks for. Once again, we are given a straight line with measures on that one side of it, so we can take 75 plus 5x minus 5 plus 7x plus 2 equals 180. Go ahead and combine like terms. We end up getting 12x plus 72 equals 180. There we go. Subtract 72 on either side, and we end up getting 12x equals 108. And this divides nicely as well, so x is equal to 9. We'll continue on. We are now going to discuss arcs. An arc is a portion of a circle defined by two endpoints. A central angle separates the circle into two arcs with measures related to the measures of the central angle. So this central angle separates our circle into this arc and into this arc, and we have special names for those depending on their size. A minor arc is the shortest arc connecting two endpoints on the circle. So in this case, endpoint A and endpoint B, the minor arc is the shortest distance between them. The measure of a minor arc is less than 180 degrees, always, and equal to the measure of its related central angle. So if this is 30 degrees, that's just random, it can't be 30, but given the size. Say it was 30. That means the measure of arc AB, notice you put that little arc on top, is equal to 30. Not degrees, just 30. Okay? A major arc is the longest arc connecting two endpoints on the circle. Notice how it is named. It's measure of a dB. You have to have a third letter in there to make sure we know we take the long way around. We know the measure of a major arc is greater than 180 degrees. Or sorry, the measure is greater than 180. Arc measures are not degrees. Say this again. The measure of a major arc is greater than 180, and it is equal to 360 minus the measure of the minor arc with the same endpoint. So it's 360 minus the measure of arc AB. Or in this case, 360 minus x. And a semicircle is an arc with endpoints that lie on a diameter, okay? So the measure of a semicircle is always 180. Once again, we do write it with 3 points, A, D, B again, just so we know which side of the circle we are going around. It's still going to be 180 either way. So we need to identify each arc as a major arc, minor arc, or semicircle, then find the measure. So, put my pencil on X, travel to Z, travel to Y. I notice that that is a semicircle. And I know semicircles have a measure of 180. Once again, it's not degrees, it's just the measure of the arc. WZ X. Notice I have to go from W to Z to X without passing over X first. So I have to go this way. This would be a major arc because it's bigger than the semicircle. And the measure of this arc we can find in a couple different ways. I know this is 90, I know this is 180, so I can add them that way. Or I can do what was stated above, 360 minus the minor arc with the same endpoints also equals 270 for the measure of the major arc. And then WX is this guy, or XW, you can say it either way. That is a minor arc because it is smaller than a semicircle. And we know that this is marked at 90, so the measure of XW is equal to 90. Okay? This next one is like basically the same. I'm going to go through it really quick. LO is a minor arc. It is also 90. MLO is a semicircle. This is 180. Measure of LNO is a major arc. And it is 270. I do need you to know that not all minor arcs and not all major arcs have either a 90 or a 270 measure. That's just how these specific examples worked out, okay? Don't assume all minor arcs are 90 and all major arcs are 270. Okay, these theorems are going to be like, well, duh theorems. They totally make sense. So let's go through them. In the same circle or incongruent circles, two minor arcs are congruent if and only if their central angles are congruent. This is saying if this angle is congruent to this angle, even if they're not vertical like in this case, these arcs have the same measure as well. Vice versa, if the arcs have the same measure, then we know the angles have the same degree. And then an arc addition postulate, it's like segment addition postulate and angle addition postulate. If you take the measure of arc XY plus the measure of arc YZ, that will equal the total measure of XZ. So it works like those as well. So we're going to use some of these to find arc measures. So find the measure of LH. Now this one doesn't really need it, because we can just find it right away. Measure of arc LHI is actually just 90. Didn't have to do much work there. On the other hand, the measure of IJK, make sure you get that little arc symbol up there, we'll have to do some work on. There's like at least 3 ways that you can solve for this. I'll try to show you all 3. First off, you can see that that is a 180. So you can take $32 plus 90 plus your missing angle, equal that to 180, and solve. And get 58 for the measure here. Now we actually want this whole thing, so then you can go ahead and take 58 plus 90 and get 148 for your measure. Another way you can do it is just notice that this is just missing this 32 part. So you could take 180 minus 32. You also get 148 for your arc length of IJK. Or, the way I originally saw it, I noticed that this was 90. So I would get 58 here. And I noticed that these guys were vertical, making this also 58. And then I added 90 and 58 from here to get the measure of arc IJK. Either way, whatever you choose, you will get the same solution of 148, okay? Similar here, find EAB. Make sure you go the correct way with your pencil. You'll notice the measure of arc EAB is also 90. Nothing crazy there. To find the measure of BCD, we can do any of the 3 ways that I just talked about before. I'm going to do the 180 minus 38 here to get the remaining bit. You can take your pick. I get 142 equals the measure of my arc BCD. Okay? Now, we are going to talk about arc length. The ratio of the length of an arc L, right here, to the whole circumference of the circle is equal to the ratio of the degree measure of the arc to the whole circle's degree 360. Okay, so if you look here, we set up a proportion. I like using the proportion more than the equation. The proportion makes way more sense to me. Where in this left side, it's the arc length over the total length or circumference of the circle equal to the degrees for the angle over the total degrees for the circle. So if we use that idea and our proportion, we can solve. So find the length of DA, arc DA I should say, round to the nearest hundredth. Now, before, we were sort of just kind of finding an arbitrary measure, okay? This is not going to be the same thing. The length is an actual distance in centimeters, meters, feet. That tells you how long a certain segment actually is. We have our proportion that I'll go ahead and write out. We just need to plug in either L, R, or X, depending on what we are trying to solve for and what we are given. I notice I'm given my corresponding central angle, so I go ahead and plug in 40 for X, and I'm given my radius of 4.5. Now I just cross multiply to solve for the length. So I get 360L is equal to 9 pi times 40. Now I happen to know that 9 times 40 is 360. And then we just tack the pi on. If you want, you can go ahead and multiply that out. We end up getting 1,130.97 is equal to 360L. And you can go ahead and divide by 360 to get L by itself. You end up getting, believe it or not, pi. Now you could have seen that up here, where you just divide by 360, and you actually are left with just L equals pi. They do want it to the hundredth, so I wrote it as 3.14 over here in our solution. Okay? Now, not everything turns out to be pi. That's just how this one happened to turn out. So don't assume your answer is always pi. Because really, we're talking not really super about pi, just that the length of this segment here, whoop, is equal to 3.14. Okay? Now, we can find the length of arc DA again, different DA though, and round to the nearest hundredth. Oops, sorry, that's not DA. This is DA. So important thing to note, just like I did right there, make sure you're talking about the right arc, and that when you write out your corresponding central angle, you're actually using this one over here, not the one necessarily given. You need to take 180 in this case, minus 28 to find out what you will plug into your proportion, okay? So we're finding the length again, so length over 360, length over not 360, length over the circumference, so 2 times pi times 6, which is the radius, equals 152 over 360. There we go. Sorry about that. Now you take 360L is equal to 12 pi times 152. So 12 pi times 152. Oops, 265, there we go. And finish solving. For your solution. If you are asked to find circumference or radius or the degree, you'll just use the same proportion and solve it for whatever variable it asks. Also, I should go ahead and put my label on these because they are actual distances. So this is 15.92 for this arc length here. So if you had an actual circular object and you were trying to find how long this part of it was, you could use this math to find it. And lastly, find the length of JL, round to the nearest hundredth. So we have our same equation, L over circumference, so that's 2 pi r, equals, once again, we need to find this missing central angle. Oops. We get 158 over 360. Go ahead and cross multiply. We get 360L is equal to a very big number. And then go ahead and divide by 360. Oops, wrong thing. And we end up getting that the arc length here is 38.61. Now a quick check we can do. We know that this is just under half of the circumference of the circle, right? So if you want to do a quick check to make sure you're in the good ballpark, you can take 2 pi times r, or 28 pi in this case, and you can decide if your arc length, which we thought would have to be a little under half of your circumference, is pretty good. And I would say we're in a good ballpark range here for our length of our arc. So our answer should be good. All right, have a great